What's this derivative? Say it again.
The negative power of the one light is that right? Three x plus one to the power 7. And 6x.
Aha. And this comes from our chain rule. I end up with the derivative of the inside again. So let's think about this backwards, because that's what an integral is. It undoes my derivative idea. I want to think about the antiderivative. Now, recognize that the thing inside, the integrand function, is what just came out of the derivative above. I know the answer to this is 1/8 3x squared plus 1 to the 8th plus c. But what if I didn't have that? How would I be able to identify this as something that looked like it came from a chain rule? When I do the chain rule, derivative of the outside, leaving the inside alone, and then the additional derivative of the inside is multiplied on at the end. So I say to myself, let's look at the relationship between the inside piece and our extra bit on the end. If I think of this inside piece, let's give it a name. I'll use the same name I used when I did the chain rule. I'll call it the ugly bit. Then I can ask, what's the derivative of that? What's the derivative of this? Exactly the 6x I want, right? Over here on the left, instead of writing prime, I'm going to write du dx. And now I think back to the end of chapter 3. I say, wait a minute. I had a trick where I treated the top and the bottom here separately. And if you think about this, that's a differential separate from any sort of other thing. Up here it was dy dx. Here it's just a dx. So what if I take this dx and put it on the other side? Well, now I've got the opportunity to make a change of variable. In the integral itself, I have these pieces. Let's take all of these pieces and replace them with things that are in terms of u. So this here, what does that become? And then this whole expression, wait a minute, that's an integral that's a piece of cake because that's just power rule. Integral of u to the 7th is 1 on 8 u to the 8th plus c. And if I do that change of variable, if I substitute what I know to be u back in here, I get exactly the answer I wanted, don't I? This intermediary step, this is integration by substitution. It is more commonly called U substitution because the default letter most people use for the thing they're substituting is U. You can call it whatever, you can use whatever variable you want, you can call it whatever you want, but this is our substitution process. So if I'm working with something that I think might have come from a chain rule, I'm going to look for this relationship between the two parts that are being multiplied, an inside and then its derivative. Example. I've got two things being multiplied. Product is hard, but let's think about an inside piece. Do I have an inside piece here? Yeah, I've got a function that's composite here. I've got cosine of stuff. So if I let the u be the stuff, I'm going to take the derivative of that. What is the derivative of x to the fourth plus 2? And if I rearrange my differential, then I can say, hey, these things are being multiplied, aren't they? That means these two pieces can be put together. Because if you're multiplying in any order. 4x cubed times that cosine stuff is the same as putting the 4x cubed at the end of the cosine stuff. So that's my du. And this now becomes the integral of cosine of u du. And I know how to do that one. Yay! What's that antiderivative? But wait, there's more. Aha. And then I can swap my u back in. Since I started with a problem in x, I want to finish with a problem in x. Ta-da! This step right here, where I figure out what my substitution is, I rearrange to get the differential, is actually the important part of this. I can't move variables, but I can mess with constants as well. I want to change this problem just the tiniest bit. I guess I ran that one dry. There are two different ways to fix this problem because I can't do the same thing I did in the previous version. Why not? What's changed? There's no 4. There's an x cubed, but there's no 4, right? So I've got two choices here. I could say to myself, what I really need is a 4. I don't have a 4. I do have the ability to multiply. But the only thing I'm allowed to multiply by that doesn't change a problem is 1. So I'm going to multiply by 1. And I'm going to multiply by 1 by multiplying by 2 numbers instead of 1 number. I'm actually going to write this by putting that 1 in front here. I left a little room so I could write it down. I'm going to write the 1 right here by writing 4 times a fourth. And Jordan, that gives me the 4 I need, right? But what do I do with the 1/4? Go back to page 410, to our list of properties for integrals. And in that giant list of properties on page 410, we had properties that we used from derivatives. And I've got this property right here. But if I have a number on the inside, I can take it to the outside. I'm going to take that 1/4 and move it from the inside of the integral symbol to the outside of the integral symbol, but I'm going to leave the 4 inside. And that's the problem we just did above, isn't it? So I know how to do that one. Because I was missing just the 4, I could adjust for that. I like this. There is another way to do this same thing. It's just a little different. There's another way to do it. But now I know how to proceed. I do this same substitution we did before. And then I'll end up with the same answer we got. With a 1/4 in front of it. So that's the exact same answer with the exception of that 1/4 floating around. Does it make sense? I multiplied in that 1, but I wrote the 1 in a funky way so I could get what I wanted. Believe it or not, this is only one way to do this problem, and it's actually not the way I was taught. So I'm going to do this problem again, right over here. And I'm going to do it just a little different. Here's my little difference. I'm not going to do any of this first. What I'm going to say to myself is I've got an inside. Let's look at the inside. The inside would be x to the 4th plus 2. And if I rewrite my differential, if I take the derivative of this, I'm in exactly the same spot, right? But the 4 isn't up here. So just like I moved the dx from the left side to the right side, let's move the 4 from the right side to the left side. Now, the x cubed and the dx make up this part. So this becomes the integral of cosine of u 1/4 du. And I will do exactly the same thing with the 1/4 that I did over here on the other side of the page. I'll take the 1/4 out front. Notice we are in exactly the same spot, regardless of which way we went about this. This manipulation of the differential is equivalent to this idea of multiplying by 1. I just don't have to know what the 1 should look like beforehand. So I prefer to do this, but it doesn't matter. You can do it whichever way you want. One of these is needed because the pieces didn't match the differential I wanted. But here I was able to make the substitution become what I had. Questions? So I made that swap for the thing on the inside, and I looked and it sucked up the derivative into that extra differential. 99% of the time, the hardest part about doing one of these is figuring out what's the inside and do I have the right differential? And if I don't, how do I get it? So let's think about something like this. The integral of the square root of 2x plus 1 dx. Do I have a clear inside part? The root of stuff. Not root of x, root of stuff. As a matter of fact, you could even rewrite this to make that clearer by rewriting it as 2x plus 1 all to the 1/2 power. Stuff to a power. There's my inside part. And so I hear in the back of my head a little rattle from this doll reminding me, oh, there's something on the inside. Okay, well, let's make that our u. What's my new differential? You'll notice I'm not always going to write du dx because I know my goal is to put the dx on the other side. So if I know I'm going to do that, I might as well just put it on the other side to begin with and just take the derivative of this. What's the derivative of 2x plus 1? Yeah, that's nice and easy. Is there a 2 out there with my dx? So I either need to put it in or I need to adjust the differential. You can put a 2 here and a 1/2 out front, or you can move the 1/2 by moving the 2 to the other side of the differential. That gives me u to the 1/2 du. And then I take the 1/2 and put it out front. Finish the antiderivative for me, please. What's my correct antiderivative here? Almost. Well, if I have u to the 3 over 2, where's that 3 on 2 go? It goes on the bottom. If you want to bring it out front, you're going to have to rip it out and flip it over. So I could write 2/3 u to the 3 halves. But then the 1/2 and the 2/3 get multiplied together. And I get 1/3 2x plus 1 to the 3 halves plus c. Dean, it is quite frequent that I see people do exactly what you just did and put the 3 halves out front. The 3 halves would come down when I do the derivative. So if I'm multiplying when I do the derivative, I'm dividing when I do the antiderivative, because I got to do the exact backwards operations. Again, my goal is to try and make sure I recognize different pieces. What's my inside bit? Okay, so if that's my inside bit, what's my differential? Or I need to write du dx on this side, one of the two, right? But now I look back over here. Do I have an 8x with my dx? I do have an x though, right? The x on top could be put over here. I could write this as 1 over the square root 1 plus 4x squared. And I could write the x and the dx over there because it's being multiplied. I can take it off the top. So let's rearrange here. And I get 1/8 du is x dx. Or over here, I could say I need to multiply by 1. And so I need an 8 and a 1/8 to undo each other, right? It's your call as to which way you want to manipulate it. But in either case, what I'm going to end up with is 1/8 integral 1 over square root of u du. 1 over square root of u, bleh. How do I fix that? I need to rewrite that in a way I can figure out what its antiderivative is. How do I rewrite it? Exactly. And now I can take the antiderivative, add 1 to the power, negative 1/2 plus 1 is positive 1/2, and divide by that new power. What do I do with the fraction on the bottom? Rip it out, flip it over. So that's going to give me 2 over 8, or 1/4. U to the 1/2. A 1/2 power is a square root. Put back in the u thing. There we go. That's my final answer. Phew. Questions? Sometimes what's inside doesn't look like it's inside. What's the inside part here? The 6x, right? Because it's e to the stuff, not just e to the x. If I were taking the derivative, that's where I'd use my chain rule. So I think of it that way. Wherever I think I might need the chain rule, that's my inside part. What's du? Do I have a 6 next to my dx? So either I need to put 1 in, or I need to rearrange over here. There. I multiplied by 1. That 1 happens to be 6 over 6. Then I take this part and pull it out front. Oop, there's no x there. There's just a 6. Careful. Got to put the right stuff down. Oh, okay. This is 1/6 integral e to the u du. What's the antiderivative of e to the u? Yay. But the 1/6 stays there. But wait, there's more. Now the dx went away, but when I do my antiderivatives, I have to get that plus c. Now I put it back in x. Questions? We did an integral yesterday with some trig functions in it. Trig functions are one of those interesting pieces because there are cases where my trig functions hide insides and outsides. Let's think of this problem again. When we did this yesterday. Wait a minute. Was it cosine over sine squared or was it sine over cosine squared? Go back and look at yesterday's notes. I just realized I'm trying to do this from memory. I think I wrote it the other way around. Was cosine on top, sine on the bottom? Okay, so let's swap those. When I did this yesterday, I split this up and wrote cosine over sine and 1 over sine. I said, oh, cosine over sine is cotangent. 1 over cosine, that's cosecant. But what if, oh, hey, there was a minus sign also. What if I don't do that? What if I instead think of this as follows? I took the cosine off the top, just like we took the x off the top in that x over the square root of 1 plus 4x squared problem back on the top of the page. I took the x off the top. This time I took the cosine off the top. Why would you do such a thing? Because now there's a relationship between these two parts. What's the derivative of sine of x?
It's
Just regular cosine. The derivative of sine is cosine. So I could make a substitution. If I let u equal sine of x, then du is cosine of x dx. And that's exactly what is sitting there waiting for me. So I could legitimately say another way to do this is to write this as negative integral 1 over u squared du. And this just became a power rule problem. Son of a bitch. Wait a minute. Why does that help me? What's the antiderivative of 1 over u squared? Oh, it might help if I rewrote that to be a power. All right, if that's u to the negative 2, then when I do the antiderivative, I get it would be over -1, but over -1 is the same as multiplying by -1. So I put the negative out front. Negative times negative, they cancel each other out. That's the same as 1 over u. Yes? But u was sine of x. So this is 1 over sine of x plus c. What other trig function is 1 over sine of x? And that's the answer we got yesterday. It worked exactly the same way. Well, it worked out to be exactly the same. We went about it in a different fashion. That's amazing. Two different techniques give me exactly the same answer. My substitution idea, my inside-outside chain rule here, is actually a really powerful tool for just that reason. But I mentioned trig functions specifically because trig functions hide things. If I go back and I look at my formula sheet, if I go to page 410 and I start looking at all the formulas for things we already know the antiderivative of, that's not on the list. I know the derivative of tangent is secant squared. I know there's a tangent in the derivative of secant is secant times tangent, but I just have a tangent. I don't have a secant to go with it. Rather than flip a table, I'm going to do the same thing we just did. I'm going to rewrite this in sines and cosines. And I'll take the sine off the top. Jack, this is where the minus signs are going to come back and bite me in the ass. That's why I need to remember which one goes which way. When I'm dealing with sines and cosines, where are the negatives, where are the positives? I have a sheet for you. Sine, cosine, negative sine, negative cosine. Power rule tells me that when I take the derivatives, I go down in power. I've written this list so that when I go down, I'm taking the derivative. And when I go up, I'm taking the antiderivative. And this loops around both ways. So if I want the derivative of cosine, it's minus sine. And if I want the antiderivative of cosine, it's sine. I just need to know which way to go. I like this. It helps me remember. Because over here, I have a cosine on the bottom. And the derivative of cosine is not sine. It's minus sine. So if I do the u is cosine of x, then du should be minus sine x dx. But I don't have a minus there. So I'm going to shove one in and put one out front. I move this minus to the other side, take the minus sign from here and move it out front. Oh, what's the antiderivative of 1 over u? I'm sorry, Jack, I couldn't hear you. What's the antiderivative of 1 over x? Say again? The logarithm, ln of x. So I'm going to get the ln of u. I can't forget the absolute value here. I need the absolute value. I need the plus c. And now I put u back in here. Now, as far as I'm concerned, you should stop there. But the textbook actually took this a step further. When you have a number in front of a logarithm, that came from a power inside the logarithm. So I'm going to think of the minus sign out front as going back in and making it 1 over cosine. Cosine to the negative first power. What's 1 over cosine? What other trig function is that? Secant. So really, by moving this inside, we get this as ln of secant of x. I'm perfectly happy stopping here, but the book actually had this answer in the back of it. Questions? Sometimes I need to use my substitution more than once. What's the inside part here? So I should use that for my substitution, u equals x plus 1. What's du?
Yeah.
1 dx. So that takes care of this. That takes care of this. What the hell do I do with this extra x? This is the relationship between x and u, right? I want everything in x or I want everything in u. So I'm going to use this relationship again. And now my integral becomes u minus 1 square root of u du. Why is that better? Because I can multiply this in. I couldn't multiply this in, but I can multiply this in. And that's power rule. Yay! Dean, this time I did the flipping automatically. It would be u to the 5 over 2 over 5 over 2. So I took the 5 over 2 out of the bottom and flipped it, making it 2/5. Same thing with the 3/2 that's on the bottom. Bring it out front, it becomes a 2/3. But I started in x, so I should finish in x. It is remarkable to think that the derivative of this ugly expression is just this. There's a lot of algebra that must have happened to go from this and take the derivative and get that. Questions? When I do definite integrals, again, there are two options based on what I want to do with my substitution and what I want to do with the limits of integration here. You have some choices. We've already done that version of the problem, right? So I know what the value of u is supposed to be to make this substitution. What's u? Okay, so if u is 2x plus 1, du is 2 dx, I don't have a 2, so I'm going to get 1/2 du is dx. So I say to myself, I'm going to end up with the integral of the square root of u, a 1/2 out in front, and a du. I just took it from next to the du and put it out front automatically. But the numbers 0 and 4, those are x numbers, not u numbers. Crap. I could do this problem, write out my answer in x, and then plug in the 0 and the 4, right? I could do exactly all the work we already did. But if I'm going to do that, I need to keep track of the fact that I know this is a different letter for 0 and 4. So what I do is I write that down here. Since I don't plug in the numbers until the very end, the fact that the variable in the integrand is different than the variable in the limits of integration needs to be kept in my head. I can't plug in until I've finished the antiderivative. So I go through the rest of this process. When I'm doing a definite integral, I don't need the plus c. So I get 1/3 u to the 3/2, x equals 0 to x equals 4. I turn it back into x's. 1/3 2x plus 1 to the 3/2. Notice now I don't need to write x equals 0, x equals 4, because those are the right letters. So I can plug that in. 1/3 9 to the 3/2 minus 1 to the 3/2. I'm going to leave that number just like that. I could simplify it. I'm going to wait to do that. That's option 1. But option 2 goes back to what I said earlier. I want everything in x or everything in u. And this expression here mixes the two of them. And that pisses me off. Not a lot, but a little. Since that irritates me, I don't like it. I want to fix it. I had this substitution right here. If I wanted to change everything, I could change the numbers. If x is 0, and I use this expression, what's the value of u? And if x is 4, then u is. And now I can say, I'm going to write 1/2 integral square root of u du, but I'm going to write it from 1 to 9. I changed the limits also. I never have to think about x ever again in this problem. As far as I am concerned, there is no x. This is a brand new problem. And the letter is now u. This is u to the 1/2. So I get 1/2, 2/3, u to the 3/2 from 1 to 9. The 1/2 and the 2/3 cancel, give me a 1/3. I plug in 9. I plug in 1. It's the same exact answer. Ooh, I like it. It's up to you whether you want to go back to the letter we started with. We have to do that with an indefinite integral. We don't have to do it with a definite integral. But if we don't, we need to make sure we switch the limits to the new variable. Questions? It turns out this is a very useful general idea. Changing the limits of integration means everything got rewritten. Two other results. Based on the idea of symmetry. Okay, wait a minute. Symmetry. We had even functions. A function that is even is the same on the left side as it is on the right side. A function that is odd, the left side is the opposite. Well, let me write it this way. F of minus x equals minus. The left side is the opposite of the right side. Pictures. Even, odd. If I am going from minus A to A, what happens in this picture? What's the total area in this picture? 0. Because the area on the left is negative and the area on the right is positive. If I'm going from minus A to A in this picture, the area on the left is exactly the same as the area on the right. So I could just cut it in half and multiply by 2. Both of these results appear here, the integrals of symmetric functions. And this makes my life easier in this case because I always get 0, and in this case because one of my limits is now 0, and plugging in 0 is almost always an easier number to plug in. So knowing about symmetry makes my integration easier. I will see you all on Monday. Have a wonderful weekend.